So the two starter problems here. Number one says express x and y in terms of theta. Let's see how you went. So with question one, we know that we always stand at the corner where the angle is made, or the vertex. And so we know that y is opposite the angle and x is adjacent. And SOHCAHTOA says that sine of the angle is opposite over hypotenuse. But I've chosen a very special triangle here, and that's a triangle with hypotenuse 1. So sine of theta is equal to y over 1. And what's y over 1? I don't know, it just is. So that means that y, so that was a little joke first thing in the morning. It was pretty good. Thank you very much. So y is like sine theta. Hiya, Jack. Does that make sense? If I need to spell it out, but I'm going to erase it, I've said that the sine of theta is opposite, which is y, over hypotenuse, which is 1, which means that sine theta is equal to y, and then I've just flipped it left and right. This is really important, so if you've got a question, ask it now. 5, 4, 2, 1, 0. Just got a blind spot with 3s. Similarly, with cosine, cosine is adjacent over hypotenuse, so I've got cos theta is equal to adjacent x over 1. X over 1 is just x, and so I've got x is equal to cos theta. So I've got these two results here that for two random variables, I can if I have a hypotenuse of 1, basically the length of the horizontal length is just cos theta, and the vertical length is sine theta. Why that's important, I will get onto a little bit later, but I want to make sure that if you've got any questions, you're going to ask them now before I move on. No? I hope that's clear, because again, this is mathematics methods foundation. If this is a foundation fact. If you don't get that, the rest of it's going to get harder and you're going to get lost faster. So I hope you've got it. I'm going to stop worrying about you now. You're going to either be asking me questions or you're not, and I can't help that from now on. Use the sine rule to find theta in this case. Okay, so you should have gone sine theta over root 3 is equal to the sine of 30 degrees over 1. Great, there's that over 1 again. So if I multiply both sides by root 3, I get sine theta equals root 3 sine of 30 degrees. Blip, blop, blip in your calculator, find the inverse sine, and you should have got, I think, 60 degrees. That's a problem, isn't it? Your calculator didn't lie as such. But look at that diagram. Does that diagram look like a 60-degree angle? Nuh-uh. And if you think about it, if that diagram was right, and I can tell you I've got the perspective fairly reasonably right, that angle there, if that's 30 and that's 60, that'd be 90, and so that'd be 90 degrees there. Nuh-uh, that's definitely not a 90-degree angle. So there's definitely a screw up here in the calculations, but there is nothing wrong with what you've done here. And the reason why there's nothing wrong with what you've done here, other than getting the wrong answer, is because we are presented with what is called the ambiguous case. Now, you don't need to learn the ambiguous case this year, but I'm using it just to point to a problem we have with sine and cosine and tan in general. And that is that SOHCAHTOA, the principles of SOHCAHTOA, assume that theta is an acute angle. That means an angle between 0 and 90 degrees. If you think about a right-angled triangle like this one, that right-angled triangle means that these two angles must be less than 90 degrees. It could be 89 and 1 or 89.9 and 0.1, but they both because these have to add up to 90 degrees and they can't be zero, they both have to be acute angles. And SOHCAHTOA is based on the angles being acute. But what you've been doing over the last couple of lessons with the sine rule and the cosine rule is you have just sort of been flexibly using sine and cosine to work out the values of angles up beyond 90 degrees. You've just been doing it. The sine and cosine rule works for it. But what we haven't done formally is we haven't come up with a way of defining or redefining or extending our definition of sine, cosine, and tan to cover angles beyond 90 degrees. And hence we have the ambiguous case. So the actual answer is 120 degrees. What's the relationship between 60 and 120? Yeah, do you know that that's right? Do you know the fancy word for that? Well done. But no, that's not what I meant. I heard the right word around here somewhere. Complementary angles. So it turns out that there's a relationship here between the, in inverted commas, wrong answer, the calculator answer, and the actual answer, and that is they're both complementary angles. They add up to 180 degrees. That's what complementary means. They add up to 180. And in practice, as Emma said, it means if you subtract one from 180, you get the other. Who cares? You'll never get the ambiguous case in an exam or test. No, it is not fine. It's not fine because what I'm doing here is I'm developing your understanding because you're a maths method student and you're not a script monkey or a grade 6 student who only just needs to plug things into a calculator. Okay, it's not fine. Because you have to make some judgment calls as to whether it's going to be ambiguous or not. It's not hard, but it's just that there's only so much we can fit into the course. That's all. That's all. Simple as that. It's just a matter of content breadth rather than depth in that particular case. Okay, so let's have a look at the next screen. And what we're going to do is we're now going to develop an understanding of what is happening beyond 90 degrees for theta. First of all, what I have done in diagram 1, I don't know what happened to the background lines, but what I've done in diagram 1, I might actually just zoom up just for the time being, is I've taken a point, a line from the origin, which means the middle here, and I've extended a line 1 unit long. I'll call it the unit line or a unit line. 1 unit, because it could be centimetres, metres, kilometres, or small pink heffalumps. It's a length of 1. And the point ends there, right, where my little red dot is. It's just there somewhere. Now, I didn't specify exactly where that point is, but what I do know is that the Cartesian coordinate plane says that that coordinate will be some x distance across and some y distance along or up. So generically speaking, I can say that that coordinate is x comma y for some value of x and some value of y. Are we okay with that? Yes? When we're writing, this is all the way back to grade 7 or 8 now. When you first came across the Cartesian plane, that's what this is with the with an axis. We call that pair an ordered pair, so that when you see it, it always means the first value you see is the x coordinate and the second value you see is the y coordinate. Imagine if it wasn't ordered and you were given 3, 5. There'd be 2 locations you could put that. So it's always the x and followed by the y, always. Alrighty. So we've got this idea of a random coordinate x comma y. I'll zoom out and leave it zoomed out now. I'll stop it, Siri. What we can also do is we can put an angle between the x-axis and that unit line. So remember that unit line has length 1, and I'm going to say this is a random angle, and I'm going to use a special format for this angle, so don't freak out about it. It is just another bit of language. I'm going to put theta there for the angle, but then I'm going to put a little, I think there's a language term for it, but in maths we call it a hat. So I'm going to call that theta hat. It's often referred to as the base angle, but it's almost always just as commonly called the reference angle. And I'm telling you both because I strongly suspect I'm going to refer to it as the reference angle quite a lot, although I know a number of teachers at this school call it the base angle. And I noticed Ryan say, for example, that's what you're used to calling it, the base angle, I think. So both of them are legitimate, but if you hear me say reference angle, I mean base angle and vice versa. It's the angle that's between the x-axis and this unit line in this area of the graph. It's an acute angle. Now, here's the kicker. On the first page, we saw that an x distance with a unit line, would have the value cos theta. And everyone said, yes, that makes sense to me. And if you said you didn't say the opposite when you should have, that's on you. And we can see that the y distance here was sine theta. So if I take that to my coordinate system, then my xy would become x is cos theta, in this case theta hat, and y is sine theta hat. And so what we've got here is we've got an angle that is formed with the x-axis and this unit line, with the vertex being the origin. Theta hat being an angle that is formed between those two, and we have a result, which means we now have cosine and sine defined as the coordinates of the end of that line. Remembering that that line has to be of length 1. It's the unit line. If I rotated this line all the way around this axis, it would form a circle of radius 1, and that's called the unit circle. And as I rotate this line, I would get different angles. Okay, questions before I move on? Okay, you've been a lovely bunch. I hope it's making sense so far. This is hard stuff, right? This is all foundational stuff which will allow you to access heaps of problems that you need to solve for the test or on an exam, right? So you don't have to repeat any of this. If you don't get it, then you won't get the rest. Joe? So is the hat just because it's sort of like... Yes, theta hat, it'll make sense actually the next thing I do, it'll make sense why I've got this thing called theta hat. Please feel free to write a note to yourself. That's what we call it, theta hat as well. So what does that mean? Well, that means that let's imagine, excuse me, I take a line, and this time I draw that line over on this side. Again, it's going to be unit length 1, and it's going to be theta hat over here as well. So I'm wondering whether it's enough to say that this triangle here that I'm illustrating here, I'll even do the dotted lines in red so you can sort of see how the triangle is formed. So I've got this triangle here, and now when I switch the sign over, so I switch the line over to the other side with the same reference angle, with theta hat here as well, can you see that this would be the same triangle? Just flipped. It's the same triangle. Great. So it's the same triangle with an xy coordinate, which must be the same lengths, right? Except the difference is that in terms of the coordinates, instead of it being x, it'll be negative x because we've gone backwards. See that? It's negative x. And this would still be positive y because we've gone up the y-axis. So this, I might actually zoom in for this just to make it really clear for you. So this is negative x comma y. Negative x because we've gone back on the x-axis, and y because positive y because we've gone up the y-axis. Good, good, good. But before we said that x is cosine of theta hat and y is the sine of theta hat. And that means that we can write this as negative cos theta hat and sine of theta hat.
How do you know to put cos or sine first? Is it
Great question. I'm just going to zoom out, switch pages for a second to answer Emily's question. We saw that in a right-angled triangle with unit hypotenuse, unit length 1, that x would be cosine theta and y would be sine theta.
so x is always
Horizontal and y is always vertical.
and x because x y always then it will always
Because yes, because the coordinates are always ordered, x followed by y, then it's always going to be cosine followed by sine. Yep. All of these are lovely clarification questions, and I appreciate them. Okay, are we right so far? So that's theta hat. But what we're often given is theta. So our extended definition of cosine, sine, and later I'll talk about tan, is that what we do is we always take the angle from this, what we call the first quadrant axis, x-axis. So if we take the angle from here and go over here, this is what we're going to call theta. I'm going to put a direction on it as well because we always go anti-clockwise. So this angle here is theta. Okay? So theta plus theta hat always equals 180 degrees. No, not always. In this instance, it equals 180 degrees. Okay? So what we have now is an idea here where we can say if I've got the sine or cosine of something between 90 and 180, so between here and here, then I can say that's exactly the same as the sine and cosine of the acute angle, the base angle, the reference angle, theta hat. It is the same as the cosine or sine of theta hat, but it's just going to have potentially a different plus or minus in front of it. Okay, so in this case, this particular angle theta, we would say that the sine of theta would be equal to the sine of theta hat, right? Why? Because the y coordinate is positive because we've gone up the y-axis. So the sine of theta, you probably need to look at what I'm doing to make sense of this. The sine of theta is the same as the y coordinate, which is sine of theta hat. I'm going to put this together with an actual example in a moment. But it also means the cosine of theta is going to equal the x coordinate, which is negative cos theta hat. Like so. Negative cosine theta hat. So we've got this happening here will get us a negative x coordinate, and hence it'll be negative cosine theta hat. So why is this important? Particularly when you've got calculators, because you're not always going to have a calculator. It's important because what we're now doing is we're defining an angle theta, which is beyond 90 degrees in terms of an acute angle with a plus or minus next to it. going back to this problem here, you may be able to see a glimpse into why this is a problem. The sine of 60 is the same as the sine of 120, because 60 would be the base angle, the reference angle, theta hat, and 120 would be the actual angle, because sine is like the y coordinate. It's the positive y coordinate. However, and you can confirm this for yourself because I'm now over time and I need to push on. However, if I did the cosine of 60, that would give me a value. And if I went the cosine of 120, it would give me the same value, but it would be negative. Okay, so let's just say the cosine of 60. What is the cosine of 60? The cosine of 60, I think, is a half, 0.5. The cosine of 120 would be negative 0.5. So the same value, but negative. And that's how they link together. Okay, I'm running out of time. So this video will be available for you to look back on. I do need to push on. We're going to use this idea then of x and y coordinates so that we can extend our definition as far as we can. So at the moment, we've got, so far we've covered from 0 to 180. Now we're going to cover from 180 to 270 degrees. So we're going to go from here, always starting from here, the x-axis, and now we're going to go all the way to here, like so. So let's have a look at the coordinates first. The coordinates here would be negative x and negative y. Yeah, we've gone back on the x-axis and we've gone down on the y-axis. Okay, so if this is theta, you'll get a hang of this. Honestly, you will eventually. This is your first grab at it, I suppose. If this big old angle is theta, this angle is theta hat. Theta hat, the reference angle, the base angle, is always between the x-axis and the unit line. So this is theta hat, this little acute angle here. So the triangle would be formed here, and x would be cosine of theta hat, and y would be sine of theta hat, but then we have to apply the sign, the plus or minus. So that would be negative cos theta hat and negative sine theta hat. Okay, so in this case, if theta is all the way along here, so let's just say it's 200 degrees. If theta was 200 degrees, well, that would be 20 degrees after 180, so theta hat would be 20 degrees. So the sine of 200 would be the same as minus sine of 20. You can actually do this on your calculator and you can see it's true. The cosine of 200 degrees would be the same as minus cosine of 20 degrees. Again, the 20 comes from 180 plus 20 to make it to 200. Okay, next one. What happens if the angle goes all the way around? Like so. That's my theta now. It's a reflex angle, right? It's between 270 and 360. If it goes all the way around here, then we will have what for x? Will x be positive or negative? Great. So positive x, and y will be negative like so. And so that would make, theta hat's in there. Positive cos theta hat and negative sine theta hat. And there's all three of them together. And I've got the fourth one there. I need to write something else in. So what we've been able to achieve from this is we've been able to achieve any angle from 0 to 360, really, and have a legitimate idea about what sine and cosine would be for those angles. So our extended definition, something which makes sense mathematically, is that we've changed sine and cosine to not only just be SOHCAHTOA, which works for acute angles, to a coordinate system where we take on this idea of a reference or base angle, we work out the sine or cosine of that base angle, and then we apply a positive or negative sign to the value because of what quadrant it falls in. And I'll talk about that in a second. Georgie.
There was a hat where theta was the cause of theta hat. Did the hat change the number, or was it just indicated as
Theta hat is just notation, and it just means the acute, the sharp angle between the x-axis and that unit line. And that's all it means. The reason why we use it and don't use alpha or x or y or z or something like that is because there's a definite link between theta and theta hat, right? They're linked together, which is why we sort of just leave the hat to say, this is the acute bit. No, it's only to describe a variable. It might be x hat or z hat or something like that, but the hat just says this is the reference angle, this is the base angle. Lovely. Good questions. I hope the video picked that up. Sophie, no talking, please, so people can concentrate.
I'm not sure if this would ever be the case, but do you know with the triangle, I'm not sure what you call it, can it ever be more than 1 unit, or because that would change the...
No, the way it's, yeah, so that's a definitional question. So by definition, the way we I mean, there are complex reasons why the definition works, but just on the surface level, by definition, we use the unit line to define this circle. Because, I mean, fundamentally, because it gives us this result. By using the unit hypotenuse, we end up with the x-coordinate being simple cos theta and the y-coordinate being simply sine theta. And knowing that SOHCAHTOA works with over the hypotenuse, having the hypotenuse of 1 means there's no complicating factors. Yeah. Okay, switching back to the last thing I wanted to talk, well, two last things I want to talk about then. Very quickly, what does it mean for tan? Let me go back to this first diagram here, and you can see that we know what tan is, right? Tan is opposite over adjacent, yeah? So tan is y, which is called the rise in a function, over the adjacent, which, sorry, in a graph. In a graph, this would be like the run. So tan is rise over run. Rise over, what's rise over run? Gradient. So if we go back and have a look at these three lines here, we can start talking about tan as being the plus or minus of tan would be based upon the gradient being positive or negative. Okay, so looking at the first one here, I'll zoom in so you can sort of see it a bit more easily. So the gradient in this quadrant, oh sorry, I'll go to this one here. The gradient in this quadrant is positive, right? Left to right, it's going up. So the gradient is positive. So we've got tan theta hat, I'm just going to say equals gradient here just for your notes. So it's positive. Yeah. Yeah, thank you. Thank you. It is theta hat just for that first one. In the second diagram, we've got, oh, sorry, I'm on the wrong, no, it's okay, I'm on the right one. In the second diagram, we have tan theta is equal to, well, what is that? Is that a positive or negative gradient? It's a negative gradient, right? It's going down. So tan theta is equal to negative tan theta hat. Yeah? So we're looking at the base angle, the reference angle, as where we get the value of tan, and then we apply a negative to it because it's a negative gradient. Next one. Do we have a positive or negative gradient here? Right? So we've got, I didn't write this down before, sine theta is equal to negative sine theta hat. Cos theta is equal to negative cos theta hat. And tan theta is equal to tan theta hat. It's positive because we've got a positive gradient. And in the next one, we've got sine of theta is equal to negative sine theta hat. Cosine of theta is equal to positive cos theta hat. And tan is what? Positive or negative? It's going down. Yep, so it's negative tan theta hat. That's a whole heap of, that's like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 12 different results there. But really, it's not that hard. Let me go back here. Have a look. In this first quadrant, I didn't write it all down, but in this first quadrant, the angle theta is the same as theta hat. It's an acute angle. So in other words, sine, cosine, and tan are all positive because it's in this section here. This section, I'm going to have to give it a name because I'm sick of calling it this section, is called the first quadrant. And I'm going to write that down, Q1, just in the corner here. And in the first quadrant, the values for sine, cosine, and tan are always positive. So I'm going to put a big A here, not for always, but for all of the trig values are positive. The next one is quadrant 2. And you can see here that in quadrant 2, nope, it's on the other page. In quadrant 2, sine is positive, but cosine is negative, and tan is negative in quadrant 2. So the only one that's positive is sine. Love to hear people saying sine to and not sin. That would be a sin. There we go. So if you love Adelaide, there's South Australia for you up the top there. The third quadrant, this bottom left-hand corner here, we've got sine is negative, cosine is negative, and tan is positive. So the only one quadrant that's positive here is tan. So for quadrant 3, tan is positive. Guess what the fourth one will be, even without looking at the answers? Sine is negative, tan is negative, cosine is still positive, and so we have the fourth quadrant, C, as being positive. This is called a cast diagram. I'll leave it for you to figure out why it's called a cast diagram. I didn't tend to call it a cast diagram, but you do have that diagram in the information booklet, so you don't have to memorize it. But again, you also don't want to have to keep on flicking to your information booklet for basic facts. So remembering that relationship, that everything is positive in first quadrant, sine is positive, tan is positive, cosine is positive in the respective quadrants is useful. Personally, I was taught, just so I'm going in the order of the quadrants, all students take care, ASTC. All students take care, quadrant 1, quadrant 2, quadrant 3, quadrant 4. I've also heard South Australia Technical College. And just for the video, I'm doing an emoji shrug because because it makes sense left to right, but it doesn't link very well for me. But having some sort of aid to memory, mnemonic, is useful for you. Okay. Let's do a little bit of verbal work. So I am quite behind. So I might end up getting through the theory, but you might have to do some of the practice work for homework, sorry. But this is just so important to get right. But let's just have a quick brain break. If you want to have a really quick 30 seconds, stand up and stretch just so that you can reset your brain. That's science. Science says that standing up actually resets your brain. Please do so. I encourage you to stand up just for 10 seconds, say hello to your neighbour, then sit down again while I get this organised. So we've just been through, just saying this for the video, we've just been through some worksheet problems together as a class. And now I want to get through how do you solve simple problems using the cast diagram. And what I have here are some steps. I'll verbally go through them, but I reckon I'm going to go faster than you can write down. But what I'll do is I'll make a PDF of these notes available to you on Google Classroom as well as the video, so you can copy them out later, even if you don't watch the video. So, verbally. Number 1, draw a cast diagram and identify where the angle lands. Quadrant 1 to quadrant 4. Identify the base angle, the reference angle, theta hat, and it's always taken from the x-axis, never from the y-axis. Theta hat is always defined from that. Number 3, calculate the trig value of theta hat and then apply plus or minus to the value. They're the 4 steps. Again, I'm going to go faster. I know you won't have had time to write all 4 steps down. So it's probably almost more important that you're watching rather than writing at the moment, and maybe catch up with your writing later. So example 1, given that sine of 30 degrees is a half and the cosine of 30 degrees is √3/2. These are exact values as opposed to approximations. What is, and we've got 4 possible values here. So what is sine of 150 degrees? So this is how we would solve that one. The sine of 150 degrees. The first thing I would do is I would do my cast diagram. And I would see that 150 degrees is going to be here. Yep. That's 150 degrees. Therefore, what's the reference angle? What's theta hat? 30 degrees. And I actually wouldn't spend any time writing calculations down. I would just do the diagram and fill in 150 and 30. Then I would go sine of 150 degrees is equal to, I leave a little space and I write the sine of theta hat, which is 30 degrees. And then I look at my cast diagram and go, CAST, sine is positive here, so I don't need to add a sine to the start here. So sine of 150 is equal to the sine of 30, which is equal to 1/2. Done. Easy as that. Number 2, what is the sine of 210 degrees? I draw my cast diagram. I put my line in where I know 210 will be, which is here. Oh, sorry. Is it? Oh, I see, because I haven't gone into full screen. Nope. So I put my cast diagram in. I see where the line goes, and so that's 210 degrees here, and the reference angle is in here, right? So the reference angle is 30 degrees as well, right? Because it's going to be 180 plus what will get me to 210, 30 degrees. And so I say the sine of 210 degrees must be the same as the sine of the reference angle, which is 30 degrees. Step 4, apply plus or minus. CAST, tan is positive here, which means that sine is negative here. So it's equal to negative sine 30, which is equal to negative 1/2. Done. Easy as that. I say easy. It is simple, but practice will get you there. Don't worry if you're going, oh my gosh, revisit the video a few times. Just go through these examples. I've got just 1 minute left, but I'm going to just beg your time just for a little bit. I won't go through example 2. I'm just trying to get through example 1, and then I'll leave it there. I'll do example 2 as a standalone video for you to watch in addition to the workbook work that you have to do. There's not that much to do, don't worry. Number 3 is the cosine of negative 30 degrees. So the cosine of negative 30 degrees. So first of all, I draw my cast diagram. I put negative 30 in like so, which means that the reference angle is positive 30 degrees. So the cosine of negative 30 degrees is the same as, leave a gap for the sign, for the plus or minus, cosine of positive 30 degrees, the reference angle. If it helps, I'll just put theta hat equals 30 degrees here so you can see it. I look at my cast diagram, CAST, cosine is positive in this quadrant. So that means cosine of negative 30 degrees is also positive, which means that, again, I was given this value. Cosine of 30 is root 3 on 2. And so cosine of negative 30 is also root 3 on 2. That's that done. And the last example is cosine of 390 degrees. I draw my cast diagram. I do 390 degrees. So I go, that's 90, 180, 270, 360. Was it 390? So 390 would be there. So that's 390 degrees, which means the reference angle is 30 degrees. And so I would say that the cosine of 390 degrees is equal to the cosine of 30 degrees. And because it's in this quadrant here, where they're all positive, that will just be equal to positive root 3 on 2 as well. I might adapt the learning schedule a bit. I'll just pause this. I don't need to